Previously, we came up with this theorem that's going to tell us how to count or numerate the number of permutations of Sn with a given cycle type. What I'm going to do next is I'm going to talk about the cycle index of Sn, and it's going to be a function that has a variable set, sort of t1 up to tn, and this is standard notation that I'm going to use this one parameter t to denote a bunch of parameters. Zn is a function of t, so it's a function of t1 up to tn. It's equal to the sum over all permutations. In that sense, it's sort of like a generating function. And I take t to the type of w. And then I'm going to normalize it by the number of permutations. So t to the type of w, this is t1 to the c1, t2 to the c2, and so on. And maybe that's worth writing down. So t to the type of w, this is just t1 to the c1, t2 to the c2, tn to the cn. So whenever we're raising a variable to a composition, we just think of our variable as actually a sequence of variables. And then this is what we get. Let's do some examples to compute this out. So the first case that we'll do is the trivial case, which is that there's one way to do nothing. Z1 we can do in our head because there's one permutation of 1. It has cycle type 1, so this is just simply t. Once we start doing Z2, it's going to get a little more exciting. So this is going to be 1/2. I have the identity, so the identity is going to have t1 squared, and then I have the transposition. So this is going to be t2. And there's nothing more exciting there. But once we start getting up to 3 cycles, it's a little more exciting. So let's think, up to permutations of 3, it's a little more exciting. So for this, let me write down the permutations of 3 in cycle notation. So we have the identity, right? And then we can think of the transpositions. So 1, 2, and don't forget to write your fixed points so that you can see them. 1, 3, that's a different transposition. 2, 3, that's a different transposition. And now we can write the 3 cycles. 1, 2, 3, 1, 3, 2. Notice all I did was switch these two, keeping the head of the table the same, just like we learned before. And so from this data, I can now write down Z3. It's going to be 1 over 3 factorial. I've got t1 cubed. You're always going to have a t1 to the n term. That's our identity element. It occurs once. Next, we have the transpositions. There are 3 of them in this case, so they are t1, t2, a 1 cycle and a 2 cycle. And then we have the 3 cycles. There are 2 of those, and they're going to give me a t3. And this is my polynomial. But I think it'll be helpful if we compute another example. So let's do 4. But the way we're going to do it is we're going to think about the cycle type and then write down what it is. So what is our cycle type? Well, we could have 1, 2, 3, 4. There's one way to do that. Now let's think about transpositions. We could have A, B, C, D. How many transpositions? So there's 1. That's why I wrote the numbers 1, 2, 3, 4. Okay, if we think about this, how many different transpositions can we have? Well, we just have to choose which 2 go here, and then everything else is fixed. So we're doing S4, so this is going to be 4, choose 2, which is 6. What's another cycle type we could have? We could have A, B, C with D left alone. How many ways are there to do this? Well, there are 4 choose 3 ways to pick the letters A, B, and C, but we also have to choose what order they come in. And so again, we saw from here, there are 3 minus 1 factorial orderings. So in this case, we're going to have to multiply this by 2. So 4 choose 3 is 4 times 2 is 8. What are the other things we could have? Well, we could have AB and CD. How many ways could we do that? 4 choose 2 ways to put the numbers there, but then we put the other 2 there. But the thing is, we could have chosen CD first. It doesn't matter what order these 2 come in. So we're going to have to divide this by 2. And that's going to be the interesting part. So this is going to be 6 divided by 2, which is 3. And then what else could we do? Well, we could have a 4 cycle, A, B, C, D. And now we have 4 choose 4. so there's no binomial coefficient there. But how many ways can we order this? So again, we're sort of pick who your head is and just take linear orderings of these three. So this is going to be 3 factorial, which is 6. And notice that this 6 and this 6 are different, but the upshot is the same. That the formula we're going to get for Z4 is equal to 1 over 4 factorial. I get a T1 to the 4th, that accounts for this guy, plus 6 T1 squared T2, that's the cycle type here, plus 8, what's my cycle type here? It's T1 T3, plus 3 T2 squared plus 6 T4. And in general, what I want to think about is what does this look like in general? How can I write down a formula for it? Well, you can see that things are kind of getting more and more complicated as we go. And what we want to do is the standard trick when we don't quite know how to write this thing down is we're going to make a generating function out of it. So what I want to think about is how can I take the sum, n greater than or equal to 0, of Zn x to the n. And now x is my usual variable for my generating function, and these t's are part of my coefficients. So I really want to think about this as a formal power series with coefficients here, and it's a polynomial, well, a formal power series in x. But my coefficients now have these parameters t. So in order to get there, I'm going to start with this, and I'm going to figure out what this is. So let's leave these examples and maybe take the more complicated example away. And we'll write the new theorem at the top. So the theorem is that the sum, n greater than or equal to 0, Zn x to the n, what is this equal to? Well, this is just, I think we'll need a little more space to write it. Exponential of T1x plus T2 over 2 x squared plus, and that's a, maybe I'll put one more term, so T3 over 3 x cubed plus. So these are not factorials. It's a little confusing when you write 2. These are honest answers. So another way to write this is exp of the sum I greater than or equal to 1 of t sub I x to the I over I. And now to give a proof of this, let me just continue manipulating this term here. I have an exponential here, so I have a sum in the exponents. I can pull that out as a product. So this is the product, I greater than or equal to 1, of the exponent of t sub I x to the I over I. So now I'm multiplying all of these e terms, but now I can think about the fact that I know what e of x is. I know what the power series of this is. So this is going to be the product, I greater than or equal to 1, of the sum of j greater than or equal to 0 of t to the I to the j, x to the I to the j, but exponents add like that. And now in the denominator, I'm still going to have, I'm going to have my I to the j, and now I get my j factorial, which comes from e. Okay, so what's happening here? Well, if we compare what we've got over here to what we have over here, this is exactly telling me that this is going to be the generating function for these cycle types. So the 1 over n factorial is canceling out this numerator, right? And then what I have down here is exactly this denominator, I to the j, j factorial. And then I'm picking up the cycle type as I go here. So this maybe here's where the theorem is and here's where the proof is. So now we have a generating function notation for this. And if I wanted to do something like, if I wanted to give an example where I'm saying, okay, how many permutations of Sn have order 6, then this means that, and the order 6 is useful when you're thinking about cycle type, because that means that every cycle has to have order divisible by 6. So that means that my cycles are going to be, they're going to be 1 cycles, 2 cycles, 3 cycles, and 6 cycles, and no other cycles. So if I think about how I'm doing this generating function, I can say, okay, well, this is just going to be the coefficient that I'm going to take of exp of T1 plus, or sorry, x plus x squared over 2 plus x cubed over 3 plus x to the 6th over 6th. And so then I just have to take the coefficient of x to the n over n factorial in this, and that's going to tell me how many permutations of Sn have order 6. So this is an application of using the generating function like this.